When I was at the Idaho National Lab, I got to meet Wayne Austad. We had a conversation here about cybersecurity as it relates to physical infrastructure. People always wonder, what if hackers shut down the power grid? They have shut down the power grid in different parts of the world, and we talk about that a little bit. But Wayne's at the forefront of figuring out, how do we secure this physical stuff? How do we secure the grid? How do we secure power stations, nuclear reactors? How do we secure all the stuff that people rely on in daily life and just take for granted? And this is the physical stuff. It can kill you if something goes wrong. It can explode. It can be a terrible disaster. And we really want to make sure that we have the best security we can for these things. Historically, it's been challenging because a lot of the physical machinery and the control systems for it predate networks, predate the internet. And so for a long time, that stuff's been vulnerable. And it's so exciting to see the large-scale operation they have at the Idaho National Lab. They have a huge team working on this. They have amazing stuff. I got to see like simulators for historical attacks on infrastructure. You can actually go and play with these things. You can see a virus taking over a power plant and shutting it down. You can test interventions. You can really experience what it would have been like to be on the response team during these actual events. It's really cool. Wayne is the CTO of National and Homeland Security at the Idaho National Laboratory. He's also the Chief R&D Officer for an operation called Cybersecurity Manufacturing Innovation Institute, CyMani. We talk about that some in this conversation as well. Wayne has a lot of very forward-thinking ideas about applying state-of-the-art technology to manufacturing end-to-end and also to this infrastructure that we rely on every day of our lives.
I've never met anyone like it.
You could hack anybody's phone in a matter of minutes. Who is that guy? Who can do that?
Talos is the most interesting man in the world.
He's one of my favorite people on the planet.
Inventor.
Wicked smart.
The master of cutting corners.
If you had a dead body in your trunk, who would you call?
He would get arrested immediately in a lineup.
I stood in line to get his autograph.
You know, his mouth can barely keep up to his brain.
I don't actually know what Pablos does.
A hacker magician.
Man of the future. 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 Future.
Wayne Austad. I'm the Chief Technology Officer for National and Homeland Security Directorate. The three things I pretty much focus on right now is we very much believe that the future of cybersecurity has to do with a blended approach between cyber-physical.
Yeah.
And don't just think about it in terms of the bits and bytes, but the actual critical function and how it's engineered, how you take advantage of physics.
Okay.
And so with that, besides just doing art of engineering, how do you formalize that into a process like that we would use if we were on the bits and bytes side, like NSA has a highly assured encryption schemes for all of their encryptors.
Sure.
And they don't worry about, for the most part,
Right.
people reverse engineering and breaking into it.
Yep.
And then how do you create the tech stack that enables and partnerships in order to enable the scaling of that type of thing.
So can you explain, what do you mean by cyber physical?
So to us, cyber physical is only useful if you can translate it into cyber informed engineering as a language we use. Cyber physical systems, people think about in terms of sensors and actuators, right? Fortunately, unfortunately, people think about it in terms of thermostats and home toaster control and things like that. But in the real world, how we close the loop on a CNC machine that's milling, or the reactors that we're controlling critical pressures and temperature, those are feeding decision systems that are now in modern systems digitized into a processor that's running somewhat of a generic software stack. Where we're going is that instead of applying that digital control technology as a last stage in the systems engineering V curve, think about your cyber enablement and how you use artificial intelligence, how you use the sensors in the beginning of the design stage.
Right.
And so to use the microreactor examples that have been previously, if you design the reactor to be inherently safe in terms of not needing safety systems to shut it down automatically, you think of it as just a nuclear fission battery, then what you're really optimizing is turning it on and off in order to make the fuel lifespan optimized or to the external power condition.
So let me try to just set this up a little bit. So maybe if you look at engineering up through the 60s or 70s or 80s even, a lot of it is like trying to design, like I got to go look at a pasta factory in Italy, and 100% of the factory, the world's biggest pasta factory, and it is all electromechanical machines, not a single computer chip in it. It was designed in the 60s before they had computer chips to aim at stuff like this. So every mechanism in there is mechanical. And you could think of, I don't know, the transmission in a Volkswagen Beetle is totally mechanical. There's no chips in there. And then if you think of, I don't know, like a wind-up timer in a kitchen from any of those eras, it's mechanical. And so the thing does its job mechanically. And then what you're saying is, all right, that era is over. The timer now is a computer, and that computer, almost by definition, creates some attack surface that makes it a liability in a cybersecurity context. And the transmission in your Tesla is now also controlled by a computer, and it is also a liability in a cybersecurity context. And going back to the nuclear reactor, we designed these reactors before. We haven't had a chance to redesign them because they have to run for a long time, and we haven't really been deploying new ones we've designed. So we've been doing these kind of strap-on Band-Aid systems and monitoring systems that we can apply on to the, let's say, perimeter of these things. But so we can watch them and we can react and tell people to react. But where we're going, both with the reactors and everything else that we're building industrially, is there's so much more of a tight integration where essentially a modern reactor is like a PC with some uranium and a modern power plant, even if it's burning coal or whatever, is a PC with solar panels strapped onto it. And we have basically everything becomes an iPhone with wheels. And so all of that just basically gets us into a point where we inherit all the benefits of the computers, but we also inherit all of the problems and the cybersecurity implications of that. Am I basically being fair at framing what you're thinking
let's
about?
divide that up into sort of two areas, right? Let's think about it in terms of the existing legacy systems we have, and where we're going with the modern digital design thread, if you will, with manufacturing. So with the present systems, right now, we could do a better job of incorporating sort of the safety mechanical systems, which you're talking about, to accommodate or use physics like in the reactor to eliminate some of the high consequence events. And then you become more comfortable using digital in new ways or artificial intelligence or other things. And so in like a power grid, that might be that to eliminate the possibility of overcurrenting a transformer, even though you're using digital relays. And then maybe somebody can attack or turn off the power, but they can't overcurrent the transformer.
Got it.
So when you do that, then you might be able to enable yourself to do more advanced digital techniques. That's one class of what cyber-informed engineering. Another class has to do with what we're doing with the Cybersecurity Manufacturing Innovation Institute, or SIMANI. And that is recognizing that in a modern engineered system that we're manufacturing, we're designing it on a CAD system, a computer-aided design, or that will do computer-aided manufacturing tool paths, and it could be additive or subtractive. And that design of that critical part is actually loaded on the end machine that is doing the end laser to do additive or cutting, run a CNC machine. And so the conventional approach to cybersecurity in terms of perimeter defense is entirely the wrong paradigm.
That's right.
Right? And so you have to think about it as, what's the critical physical feature or critical temperature in this manufacturing process in order to achieve original design intent? And then come up with the formalisms that describe that cyber-physical parameter. And besides using encryption as you send it down to the machine to do it, and authentication and all those things, how do you validate that through all processes in manufacturing? That's what we're doing in terms of the Cybersecurity Manufacturing Institute, thinking about cyber-physical. To credit our wireless division, they did this already, say, in their wireless communications platform that they call WSCOM. What they thought about in terms of a security aspect was, how do I characterize a communications channel between you and I that is unique between the conversation between myself and her? And if I can do that, becomes a base part of the security mechanism. And it's a problem I already have to solve mathematically if I want efficient communication between it. So by doing those two things at the same time, you have both a more efficient communications mechanism
Yeah.
and you have a more highly secure communications mechanism because we can uniquely characterize the comms channel between us.
Like, I guess an analogy for that might be adaptive compression or something where, you and I over time have conversation, we develop our own vernacular. I don't know, my teenage daughter has jargon with her friends that I don't understand, but it's like a shorthand that refers to something much bigger. I don't know, maybe whereas that would be different for every scenario. Going back to the encryption analogy, I think encryption is interesting because it allows us to make these kind of self-enforcing protocols where math ensures the integrity of the objective. And we can do that to craft different protocols. Some are just encryption for communication, but if you think about what is Bitcoin, for example, is a cryptography-based protocol that ensures that everything is done with integrity and fairly and no one can cheat and all that kind of stuff. And so what you're thinking of is how do we extend that model and say, all right, in some contexts, we could, the math might be the laws of physics where we're designing a reactor core so that if the water stops flowing, the thing can't melt down because of how we've designed it so that gravity would just cool the thing somehow. I don't know. Are you trying to make a language that the engineers could use to design things that have these properties, or you just looking to cherry pick opportunities to do that? I don't really understand.
So from your background,
Yeah.
you're probably familiar with the computer science terms of formal methods, right?
Okay,
Where you
sure,
do-
yeah, great.
Where you do mathematical formalisms to
Okay.
describe the logic, and then you try to have your models and your proofers to try to
Yeah.
implement those and prove that you've implemented in the fashion as you intended.
Okay,
And so if you extend that concept
yeah,
to not just the bits and bytes,
Okay.
but also to the engineering side of things,
yeah,
we do calculations all the time
Right.
in order to prove engineering, but it's usually partial differential equations and other things. So what this laboratory is doing is using the computational power of deductive logic-based formal method,
okay,
inductive machine learning type artificial intelligence,
yeah,
with the physics type models of what you do with, say, solving partial differential equations for thermodynamics or
Yeah.
computational fluid dynamics and other things. And with that view, you have an appropriate context of what you're trying to enforce through the design
Wow.
and operations lifecycle.
Wow.
So it's really creating, people overuse the term interdisciplinary.
Yeah.
And what they really usually mean
Yeah.
is multidisciplinary, where
Yep.
people from different professions are sitting at the same table doing a creative solution. If you're truly transforming the industry, you're doing interdisciplinary, in which we've created a new cyber-informed profession, if you will,
Okay.
where the power grid designers actually can think about from the very start of how they design the protection on the transformer, how they're going to wield the control function of it using these advanced artificial intelligence techniques or whatever,
Okay.
and still enforce the safety property that they want to see.
So if I was imagine this would manifest as plugins for CAD software or something that help me as I'm designing something, help me keep track of, like, I have plugins for CAD software that tell me if the thing I'm making is manufacturable
Right.
on a vertical mill. Can you take this formalism, embody it in like a plugin for CAD that says you're designing a thing that can't be deployed safely or could be deployed but would have these safety breakdowns that you're exposed to or something like that?
Yeah, that's you've hit the nail on the
Okay.
head. The challenge with formal methods,
Yeah.
and if you're familiar with all the logical structure and proofs that they put in,
Okay.
it's really abstract
Yeah.
and takes a lot of training and the only way we're going to succeed in this is by making it orders of magnitude easier. By applying it, you make it orders of magnitude harder for the adversary or orders of magnitude harder to go into a failure mode that would be an unacceptable consequence.
Yeah.
But you have to have that tool chain that makes it orders of magnitude easier. And how do you do that? Yes, you have to have these add-ons that go on to the tools that people are already familiar with,
Yeah.
but have been well vetted through design of experiment or
Sure.
laboratory experiments or other things. And that's how we're approaching
Wow.
the cybersecurity challenges in our high assurance industrial systems initiative
Yeah.
to try to fuse cyber-informed engineering and style formal methods
Yeah.
into something that is usable for the end user. That's been
Wow.
the great flaw in cybersecurity in
Sure.
in the current opinion of the U.S. government,
Interesting.
in that we're pushing all of it to the end user. Now,
Right,
the end user
right.
may be the engineer that's applying this
Yeah.
digital technology on the relay, or the end
Yeah.
user may be the guy clicking on the link.
Yeah.
But you're never going to secure things
Yeah.
against a intelligent, co-adaptive intelligence adversary
Yeah.
unless you design it from start, if you will, and
So
you have
it's
high
so
assurance
fascinating to hear this perspective. My experience with this maps back to in the 90s. We were trying to figure out how to keep the internet from going off the rails because we were just adding all these dumb shits to the meaning, my friends were getting added to the internet and they didn't know anything about computers and they didn't know what they were doing. And we realized they're just sitting ducks. This whole security problem is going to be insanity. And the way that we thought we could head that off, and also a bunch of other evils, people trying to control the internet, maybe whether that be corporations or countries, what we thought was we could architect these protocols that would preserve the security, the privacy, the freedoms, the things that we thought were important on the internet. And that really was the origin of using cryptography online. And we were the renegade version of this. So maybe that you could think of the NSA as the government version of this, but we tried to make protocols like using SSL in the browser to encrypt between a browser and a web server, but also things like encrypting email. So we had projects like PGP, which was an early email encryption thing that was over-engineered, I guess you could say. But we had more success with things like BitTorrent as an example of a protocol. It's unstoppable because the rules are embodied in the math of cryptography, and you can't break it any easier than you could break the cryptography. And then, of course, that logic has been extended to things like the Tor browser and the dark web, and also, of course, Bitcoin and some of the descendants. And those are, I think, encryption serves mainly as a analogy for you, right?
in one sense, but in another sense, just like public key asymmetric cryptography really had a big impact. The concept that we can have different keys, we don't have to share them, but we can still have a communication
because we come from zero.
Is fundamental. Same thing with fully homomorphic encryption. Because that is I don't have to decrypt the values in order to process it. And so I don't need to know what your medical records were in order to process it over this system. Problem is it's computationally challenging.
Well,
we're solving that one, right? DARPA's got some programs. Intel in a couple of years is going to have the FHE accelerators. There's lots of people working on innovation.
And a huge subset of what needed to be homomorphic in our notion is now possible just with zero knowledge proofs and being able to do.
But think about the fact that for some of the algorithms that they use in fully homomorphic encryption or FHE, some of them are very similar to an optimal control problem. In terms of how we're solving the polynomials and other things. So just like that communication story I told, if we start looking at an optimal control problem and implement an FHE loop, then all of a sudden we have inherent authentication between the sensor and the actuator.
Very interesting.
And so that's solving the low-level control problem of we have an inherent trust layer right now. And so those are the types of things you can do at a micro level or at a macro level.
I get it. That is super exciting. Is there any example we can use, or a simple example that we could use to try and make this clear for people who are listening that comes to mind for you? Like an example of a sensor and an actuator loop that
So right now, we have one of the hardest challenges, and you see this in the struggles of Internet of Things architectures and protocols versus the classic control structure of sensor, actuators, supervisory, and other enterprise levels.
Which we would hard code into firmware and leave it there.
And the real challenge, besides all protocol challenges and whether people are doing dual factor, is at the lowest level, when the command is issued from the actuator to the sensor, there's an inherent trust model that the sensor or the actuator of the sensor, we trust the sensor reading, and the actuator trusts that the command came down. So when you start putting things like FHE or this was system intent, say it's a digital twin and not a design,
Yeah.
in terms of the command, when you have that structure in place of this was the original intent,
Yeah.
and here's how we're processing the command all the way down to the lowest level, but without ever decrypting it,
Yeah.
then you get an authentication mechanism that then solves that bottom layer of trust. Because right now, if you hit an emergency stop, say your system is hacked and you want to hit the brake or whatever else, you don't ignore the brake just because you think somebody's in your vehicle.
Yeah.
You have to follow it.
Right.
And so that ends up being a denial of service attack. And so you have to deal with that lower level of trust to the actual physical signals and try to correlate it to system intent as well as command intent at the lowest level.
So do you think we'll end up needing to have a sensor like a thermometer or a thermostat sign the data that it's sending out? Like I need to, like before, because if I'm going to have an actuator that's, I don't know, going to turn up the heat, I want to really know that the sensor that's telling me that it's time to turn up the heat can be trusted, or that's not some other sensor. I'm not getting one from Alaska. I'm getting one from Hawaii. I'm getting the actual data from the actual sensor that I know is in position, and maybe the last time it was serviced. I don't know. Is that where it goes?
It's where it has to go, but I think we have to broaden what we mean by sign. Right? If you say sign right now, we're going to throw a very computationally intensive public key algorithm at it, right?
Yeah.
FHE is also computationally intensive, but if you fuse it to how you're solving the control loop equation, you're doing two things at once. But it's not just the communication side of things. The endpoint has to be formally verified. Part of the efforts is how do you create a reasonable tech stack, if you will, in order to use things like the formally verified SEL4 kernel, right? Wonderfully $500 million worth of DARPA investment collectively across lots of programs. But entirely unusable for the average programmer.
Right.
And so part of what we're working with is working with companies like Crichton to create that platform that humans can actually program and use.
Interesting.
What is a very formally verified embedded system that then goes into your sensor. So then you have high assurance endpoint sensor combined with high assurance encrypted or signed like communications.
Right.
But they're structured according to the nature of the physical process going on, and not some mathematical abstraction that you came from the bits and bytes. That didn't have anything to do with your physical situation that was going on.
Wow. Super exciting. That seemed very ambitious to take all that on.
It's why it's a research.
Yeah. Amazing. You feel like you're making real progress with it, though.
We are. Like for SIMANI, the Cybersecurity Manufacturing Innovation Institute, we have those cyber physical passports being generated in the CAD files and CAM files.
Wow.
And we have piloted in systems at Oak Ridge National Laboratory running the software on a real manufacturing floor, how we real time while the machine's going on, whether something has varied from design intent. As the machine's operating. The fun part of that, besides from a techie standpoint, is if you're familiar, with the challenges in advanced manufacturing, one of the things is like what was described here. How do you qualify the parts? Because part of the qualification is what was the temperature of the laser while you were melting these two particles together. And so you have to be able to real time, be able to vet that intent all the time. So part of the economic benefit is this cybersecurity system, the cyber physical passport, gives you a way to do that. And so now your cybersecurity investment is not just a risk avoidance or a cost center. It's bound to your actual QA, QC profit
assurance.
Amazing. So your cyber investment is bound to how you qualify your parts for NASA or for an automobile.
Great. That's super cool. It's so fascinating to think about. If you just take all that and apply it to other contexts, imagine like food security. Like we can't even do what you're describing for a burrito right now. I don't know, growing with a bunch of pesticides that I'm allergic to. Was the beef actually grass fed? Who knows? There's like everybody claims everything's high quality, but the truth is so far from being manageable. And I think there's a bunch of other contexts like that. So it'd be very interesting to see if you can succeed at making this work and you can get the overhead down to the point where, like you say, mere mortals could use it, or at least mere mortal engineers could use it, then maybe it can start to affect not just how we do energy system engineering and deployment, but also like other industries as well, automotive or aerospace, or just all these things that we're doing could really inherit that superpower that you're building.
Yeah, and we would refer to it as data provenance, right? And a purely data thing. But instead of blindly trying to collect all possible data, think about what's most important in the beginning, right? Is my milk rotten and the sour cream going in my burrito? Or is there bugs ground up into the flour that's going into my tortilla, right?
Sure.
What are the most important things?
Yeah.
And then being able to have the provenance as you're going through the system to assure that.
Yep.
Don't try to do everything.
Okay.
That would, this is almost a religious advocate. Don't try to collect everything, right? Because otherwise you'll be doing data centers and consuming lots of power, but what's most important?
Yeah.
And then have high assurance on the provenance of the information going through.
Do you ever think maybe you're going to lose on that argument? Like we might just collect everything?
The market certainly will do that. If you're pushing a particular technology, that's the easy approach, collect a lot. But I think in critical functions, what we've learned is the physics context matter, right? And if it's a health system, it might be the biological context matters. So think about that. And it may not be as much upfront design or thinking time or algorithmic design as you might think. History shows that doing it after the fact is usually orders of magnitude more complicated. Doing software, putting after the fact fixes on software, we know is 2 orders of magnitude more expensive than doing it right the first time. It should also translate into other domains.
Basically described the entire history of cybersecurity.
Market push, right?
How long have you been doing this here?
I've been at the laboratory 32 years.
Oh, wow.
Which is pretty much my career.
Oh, wow. What were you doing at the beginning?
The very beginning of my career, I had a brief stint in the oil fields with Conoco in Texas. But for most of my career, I've been here. And as I tell interns and others, I've been under the same umbrella, but I've had 5 different technical professions and half a dozen different management professions.
But in the role you're in now, you're really interfacing with other entities outside the lab quite a bit. I think you said Oak Ridge and some others are.
Part of the scaling has to be these consortiums of industry, national labs, and academia. Because you don't modify a tech stack unless you're dealing with the industries that are building the tech stack, the industries that are integrating the tech stack. And from a laboratory standpoint, the only usually industry wants to see you de-risk that. We can talk about using formal methods on the manufacturing floor, but until you actually prove that you can do it in an economic fashion at scale, and that's why we have these test ranges, and mini reactor deployments, and manufacturing demonstration facilities, because that's how we as a nation de-risk things. And that's why Bill Gates actually chose a lot of our assets here
of course,
as part of validating the concepts associated with the reactor that you're very familiar with.
That's great. As far since I got you here,
captive audience.
I know. I'll let you go in a minute, but I just wanted to give people a sense of, I feel like it took me too long to get here and see what's really happening at the Idaho National Lab, because it's a lot. It's very impressive. It's not just nuclear reactors. It's a whole bunch of things in renewable energy, all these other things going on. For people outside who haven't been here yet, what would you want them to do? Look at your website, come visit. Who do you wish was coming? Do you wish Fortune 500 companies were coming here and trying to interface with you guys? Do you wish college students were coming here? What do you think would be valuable to you guys as far as connections outside?
This will sound overly simplified, but for the mode we're in right now, what we really need is the new talent that wants to work on the challenge, independent of the profit stream or the number of devices that you manufacture.
It's hard.
And I think the current generation of graduates and many that have been through the venture capital cycle and doing some very creative things, but there is a pace to that in terms of getting to profitability that sometimes guides you away from solving the fundamental challenge.
That's for sure.
You get into the market push of the technology as opposed to, here's the hard challenge. Here's how you can contribute with a really creative team. Now, sometimes that's going to be, I wish we could hire 10 power cyber engineers from the university right now.
I get it.
I made that offer to the last university that you can come up with 10 U.S. citizens that are blended across these two professions. I'll give them a job offer right now. You don't have that. But it also means
and they're busy writing
some
spam filters for
transformative
Google
industry
anyway.
folks that want to try to break that cycle of technology push. And if I just spent whatever it is, a few years or 5 years with the laboratory,
Yeah.
I could transform the technology in this area.
Right.
And then I came from industry and I know how we might deploy it. That'd be the things that I've been looking for.
Amazing. Yeah, a lot of opportunities here, I'm sure. And plus, people get to live in Idaho, which is amazing.
Yeah, we can hire every fly fisherman and skier or
I mean,
outdoor
I think-
hiker that's out there
I
that
think
wants.
people from the West Coast might be refreshingly surprised at what the lifestyle here is like. It's amazing.
I was so irritated when another stoplight created a 12-minute commute to my job. So
Yeah.
it took me years to get over that.
Yeah, I get it. Thanks a ton. This is really great for us. I think we got to do more of this and get people to see what's in behind the curtain here. So
Thanks for coming out and
Appreciate it. Yeah, of
participating
course.
in Innovation Week, and
yeah,
thanks for your work in the. I listened to some of your podcasts.
thank you.
on-
Yeah, there's more
on
coming.
some of the
and-
nuclear side of
Okay,
things,
sure.
if you will, trying to get your
Yeah, we're just trying to.
slant and views.
Yeah, I have a lot of opinions. That's not the important part. It's more about trying to help everybody learn as much as possible so that we can advance from the state of the art instead of these old stories we have in our heads.
Despite my picking on VCs, thank you for
It's
your
okay.
contribution.
That's all right.
contribute
I'll
side of
take the
things as well.
blame for my part of it. But I'm just trying to
It's
co-opt.
an important part of the
I'm trying to
system.
co-opt the machinery of VC and aim it at the important stuff.
Yeah.
So hopefully I'm one of the good guys.
And that's part of what we tell the universities and others is that the labs usually have a pretty good view of what the hard challenge is,
Yeah.
either because of the threat coming or because we know we can mod and sim this, or
Yeah.
we've tested this. And so we want to see more of those, whether it's VC or industry or
Yeah.
university partnerships, that here's a hard challenge that we really need you to focus on.
Yeah.
Spend some time on this and break your cycle of either pure academic research or
Yeah.
a market push.
Yeah.
And when that works, it's very productive. when
Yeah,
that
there's
happens.
I think it's one of these things where like VCs can only do one part of it because they do have tight commercial constraints on what they do. And that's just the nature of that business. There's certainly opportunities to bring some of the developments from the lab and commercialize them that are very VC compatible. And then on the other side, I think I have work to do on this as well, but just try to figure out, we see so many technologies that come from other places, other universities, other labs, other parts of the world. Sometimes it's crazy hackers in the basement, but I need to figure out like, how do we get your view of those things? How do we get your insights and say, that looks cool, but we actually know of something better, or we know how to make it better, or, oh my God, that's the most amazing thing we've ever seen. That would actually be very useful to get some bridge going there.
Some form of innovation
Yeah.
incubator. You
I
leaving
will.
or are you spending any other time?
Tomorrow I get to go out and see the reactor. I'm really excited about that.
The advanced test reactor.
Yeah.
Yeah, that's a unique design.